Our galaxy has a very active center, and vast magnetized filaments of gas and dust spread out from the galactic center through the central molecular zone and beyond. They can be hundreds and sometimes even thousands of light years long. And similar structures have also been found in the intercluster media of distant galaxies. In most galaxies, including ours, the galactic centers are blocked by dark molecular clouds such as Barnard 68, and they keep us from seeing the galactic center in ultraviolet and visible light. So our observations are limited to the X-ray, radio, and infrared spectra. This image is a composite of those spectra interpolated into visible colors. Some newly published studies look into the dynamics of these filaments, how they're formed, how they're lit up, and how they might change over time. I'd like to talk about filaments both within and outside of our galaxy. I'll explain how they emit light and some of the mysteries they're already revealing about our galaxy and others. So let's get into it. I'm Cameron and this is my channel. Welcome to the Sexy Universe. The first observations of filaments in the Milky Way were in the late 70s and early 80s, and they used the Very Large Array in New Mexico. It has 28 radio telescopes, 27 of which are active at any time. There's always one that's out for maintenance, and they go through them on a rotating basis. Each of those telescopes is 25 meters across, and that gives the array a total observing area of 142,600 square feet. And the first study that was published only found what we know now are the longest and brightest of the filaments, and only the ones that were lit up in radio waves. Since then, hundreds of studies have been published. With modern instruments like Meerkat and the Chandra X-ray telescope, the quality of observations has greatly improved, and better data analysis has allowed us to make maximum use of those observations. The filaments are lit up by non-thermal processes, and what that means is there's no fusion going on like you'd find in a star. Primarily, they're illuminated by synchrotron emissions, and the energy source for those emissions is electrons traveling at very fast, relativistic speeds. When atoms are struck by high-energy gamma rays or X-rays, or when they're superheated in an accretion disk, the electrons get so energized that they leave their orbitals entirely. The electrons and the atomic nuclei they've been separated from are shot off in different directions at very high speeds. Since a nucleus is at least tens of thousands of times heavier than an electron, the electrons move much faster. Their speeds can be so high that they approach the speed of light. Electrons in this state are called relativistic electrons. The nuclei which have been stripped of their electrons and sent flying are called cosmic rays. The relativistic speeds these electrons achieve are typically described as a percentage of the speed of light. The point at which a speed is considered relativistic is when the experience of time for the object traveling at that speed is significantly different from the experience of time that an observer would have. Think about a basketball player dribbling a basketball on a platform. If the platform is still, the ball only has up and down motion, and it looks the same to both the player and an observer outside of the platform. But if the platform starts to move, the motion of the ball looks different to the observer. It would have both the up and down movement plus the horizontal movement of the platform. But to the player, the ball's motion would appear to be no different. It would still be moving just up and down. From the player's perspective, the path of the ball is shorter, so his experience of time is slower than it would be for the observer. As an object approaches the speed of light, the effect becomes even more pronounced. This is a basic description of Einstein's special theory of relativity. Relativistic speeds are achieved when an object has a change in its experience of time by 1% relative to an observer. So the slowest relativistic speed is 14% of the speed of light. Ultra-relativistic speeds are defined as speeds where a particle's momentum becomes more important than its mass. This happens at about 95% of the speed of light. So relativistic electrons move at somewhere between 14% and 95% of the speed of light. So somewhere between 26,000 and 177,000 miles per second. Synchrotron emissions are created when charged particles moving at relativistic speeds cross over a magnetic field. The field changes the speed and direction of any charged particle that comes within range. That change in speed and direction results in some energy loss. In the same way, some energy is lost when you push the brakes or change direction in a car. And just like friction within the brakes on a car produces heat, the energy from those charged particles is released as photons of light. The type of light emitted depends on the change in speed and the angle at which the particles are deflected. And it can be anything in the range from radio waves to X-rays. The galactic filaments are magnetized, and in fact they're held together by magnetization. So electrons speeding through them emit photons throughout their entire journey. Filaments in the Milky Way mainly form in the galactic center and extend out into the central molecular zone. The central molecular zone is an elliptical region about 1900 light years on its major axis. Gas and dust from the rest of the galaxy fall into it along the galactic bars, these two structures in the lit up region. The material is pulled by gravity that comes from the galactic center and our galaxy's supermassive black hole, Sagittarius A. At the same time, gravity is dragging material inward. There's also pushback from stellar wind and heat coming from all the stars and accretion disks in the galactic center and the central molecular zone. And the filaments are created as a consequence of these processes. What happens is that small clouds of material are hit by X-rays and other ionizing radiation. Stellar wind and heat create a backward push on the clouds. At the same time, the ionizing radiation is spreading charged particles through those clouds, and this has a magnetizing effect. The magnetized particles have enough pull on each other to keep them from flying apart, even as stellar wind, pressure, and heat from the galactic center pushes them backward. Eventually, all these forces operating on the outside of those molecular clouds mold them into long filaments. There have been a few recent studies of the central molecular zone and some of the cool stuff that goes on there, like star formation and molecular cloud activity. I'm working on a video about it that I plan to drop within the next week. And if you'd like to hear more about this incredible part of our galaxy, make sure you hit the subscribe button so you don't miss it. Like I mentioned at the beginning, the first observations of galactic filaments happened in the early 1980s, and the first study was published in 1984. But with new telescopes, better computers, and better mathematical algorithms for filtering out the noise, we're getting a better and better idea of where filaments can be found, how long they are, and how they're oriented relative to the galactic plane. The filaments are classified as long or short based on how they look in images. An obvious shortcoming of this is that a short filament could look larger than it actually is if it's closer to us, and long filaments could look shorter than they are if they're far away. But the region where these filaments are mostly found is only a couple thousand light years across, and the distance from our sun to the center of the Milky Way is tens of thousands of light years. So the relative distances are just too great for these effects to be all that important. So filaments with an apparent length greater than 66 arcseconds are classified as long filaments. They tend to be oriented in directions that are more perpendicular to the galactic plane. And since they're longer, they tend to emit a wider variety of wavelengths of light. The short filaments take up less than 66 arcseconds, and their angles relative to the galactic plane are more haphazard, but they are slightly more likely to be parallel to it than any other direction. They also tend to release smaller spectra of light, and in fact, some of them are only detectable within a narrow band. Astronomers break the galaxy into 4 quadrants. Because of the direction the galaxy turns in, objects in quadrant 4 are moving toward our solar system. So the images we see from that quadrant are blue shifted. A subset of filaments being blown toward quadrant 4 are oriented in a cone, and that cone points towards Sagittarius A, the supermassive black hole. And since they're blue shifted, we know these filaments are still turning along with the rest of the galaxy. The area of the cone also includes the Sagittarius E molecular cloud and some heavy star-forming regions. This cone is evidence of a powerful solar wind or a jet emanating from Sagittarius A that's going off in that direction. The researchers developed a mathematical model of the outflow into the cone. While it's just a preliminary hypothesis, their model estimates the outflow of material to be about 1/10,000th of a solar mass per year, and that it's been going on for a maximum of 6 million years. We're about to switch gears and talk about filaments outside our galaxy. So if you're enjoying the video, now would be a good time to click the like button and put your thoughts in the comments section below because it helps the YouTube algorithm. This is the poor galactic cluster Abell 194. It's located in the constellation Cetus, which is right next to Pisces. This cluster includes the normal galaxies NGC 541, 545, and 547. It also contains a large molecular cloud that's called Minkowski's object, and these large lobes make up the irregular radio galaxies, 3C40A and 3C40B. The cluster's redshift is 0.18, which corresponds to a distance of about 250 million light years. The gas and dust structures in this cluster are also lit up by synchrotron radiation. And you'll notice that these clouds are the brightest near the regular galaxies. And it's because these galaxies' active nuclei are cranking out massive amounts of X-rays. And with better imaging, lobes and filaments like this are being found in every galaxy in our local universe. These structures are called the E-Filaments. And as you can see, they stretch hundreds of thousands of light years. And they're the result of tens of millions and possibly hundreds of millions of years of gas and dust outflows from the active galactic nuclei within this cluster. And their structure and length are constantly changing as the forces from outflows toward them and magnetizing forces within the filaments act in opposition to each other. Sometimes a jet or a molecular cloud from one of the nearby galaxies passes through. Events like these cause the filaments to bend and curve, like you can see in this diagram. At the same time an object bends one of the filaments, it also leaves some material behind, allowing the filaments to extend out even further. Studies like these are showing that the filaments within galaxies and the filaments outside of galaxies appear to have the same origins and dynamics. Their lengths, orientation, emissions, and shapes are indicators of the gas movements and energy dynamics within galactic centers. And since galactic centers are almost impossible to observe directly, filaments are proving to be another important window into dynamics that are going on within our galaxy and in others. They're also visible indicators of material flow in and around galaxies. And while we know they harbor both relativistic electrons and cosmic rays, our understanding is far from complete. We also don't know how the filaments affect the regions immediate around them and perpendicular to them. These are all areas for future research. I believe the ideal life is a non-stop process of learning and growing. Thanks for learning and growing with me. If you have any thoughts or information you'd like to share, please put it in the comments section below. And don't forget to hit the like and subscribe buttons on the way out. Stay on your game, and I'll see you next time on The Sexy Universe.